A force of 46.3 pounds is applied at an angle of 34.8 degrees to the horizontal. Resolve the force into horizontal and vertical components. So, here's what we're going to do. We're going to draw a vector. And obviously, a vector will have magnitude and direction. A vector will be needed for the force. So the force is applied toward in a certain direction, right? It starts from a certain point and it's applied in a certain direction. So we can treat the force as a vector that has a starting point to the terminal point, right? At the point at which it arrives. Now, magnitude and direction. So the magnitude in this case is going to be the strength of the force, and the direction will be determined by using the angle at which the force is applied relative to the horizontal. Okay? So magnitude, I'm going to write this here. Magnitude, and this is direction. That tells you where this vector with the arrowhead will go, right? So let's draw everything together. Now notice that every vector has its components, its vertical or horizontal components. And I'm going to explain something very interesting actually, because this component can be treated as a vector itself. This component can be treated as a vector itself. And then the vertical component can be treated as a vector too, believe it or not. Okay, so it goes from here and it arrives at the final destination, at that final point. So if we label this as F, the resultant vector, which shows the force moving in this direction that has a magnitude of 46.3 pounds, we can break it up into individual vectors. We can break it up into F1 vector, or the horizontal component, or we can break it up into F2, the vertical component. Okay? So as you can see, there's a horizontal vector and there's a vertical vector. Now, there are a few relationships that are very important to realize, just so that you're not confused about the formulas. So, first notice that vector F is the sum of two vectors, right? F1 plus F2. Okay? So basically, F is going to have these components, F1 and F2. And if you sum them up, you will get this. F1 has components what? F1, 0, right? Because it doesn't have any vertical components, this vector, right? It's a horizontal vector. So it only has its own component F1 for the horizontal. Plus 0, comma F2, right? Because the vertical vector does not have any horizontal components. It just has its own vertical vector. Right? And notice that when you add, you're basically adding the respective components together, right? F1 plus 0 plus the first 0 there, comma 0 plus F2, right? So you're arriving at F1, comma F2. Okay, so that should make sense. Right, so this shows that this formula indeed holds, right? F is equal to F1 plus 0. Now, when you're speaking, this is only the components, right? This only shows you the vector, right? This shows you the direction, basically, right? Now, the magnitude, denoted by this, by the single bars here, the magnitude is the length of this line segment, right? From the starting value, from the starting point to the ending point. Right, so the coordinates of this are F1, F2, okay, of this point. So now the magnitude is the length, and the length will be determined by using the Pythagorean theorem, right? So the Pythagorean theorem is F1 squared plus F2 squared. But you might say, wait a second, What about F1 and F2 by themselves? What is the magnitude of F1? Well, I'm gonna give you an experiment. I'm gonna show you an experiment. So the magnitude of F1 can be determined using its respective components. What are the components of F1? F1 comma 0, right? So we can do the same thing using the Pythagorean. F1 squared plus 0 squared. And what does that give you? That gives you F1 being squared, but it's square rooted, so bingo, F1. So when you talked about horizontal components, the magnitude of it is just simply itself, F1. It doesn't make a difference. Okay? Now, when you're talking about F2, it's the same thing. The magnitude of the vertical vector, or the vertical component of the main force vector here, is going to be what? It's going to be the square root of 0 squared, because that's the these are the components of the second vector. They're right here. So the 0 squared plus the second component, which is F2 squared. So that gives you what? That gives you F2 squared, which is itself, right? Because the square root of the squared lets you go of the square and the square root, so you get this itself. So the magnitude of F2 is simply F2 itself. So you can treat it as components, and you can treat it as individual vectors, right? The horizontal vector and the vertical vector. In any case, I just wanted you to see, because we're going to be using an important formula that will sometimes confuse certain students. So notice that the magnitude is given here, right? So the magnitude is 46.3. And also this is a right angle, because between the vertical and horizontal, there's always a right angle. Perpendicular relationships. Now also, when it comes to direction, there's going to be an angle theta, which is going to be 34.8 degrees. That tells you where this arrowhead is going to go, where this vector will go, right? Because the higher the angle, the greater this angle going to be, the different direction will be for this force vector, right? So the magnitude is 46.3, and we have to find individual vectors, okay? Individual vectors or magnitudes of them, right? It's the same thing. The magnitudes of them and the vectors themselves, they will be the same thing, right? Because the magnitude of F1 is F1, the magnitude of F2 is just F2. So now, how do we do that? We can use trigonometry, right? We know that F1 divided by the magnitude of F, and like I said, don't be confused that I'm not using the bars, because I just showed you that the bars of F1 is equal to F1, right? That's why I'm not using the bars, to give you the magnitude. So F1 divided the bar of F is equal to what? Is equal to cosine of 34.8 degrees. Why cosine? Because this is the adjacent side and this is the hypotenuse when we're talking about a right triangle. And for the vertical component, or the vertical vector here, is going to be F2. Once again, don't get confused, because the magnitude of F2, the length of it, is itself, right? The F2 is the vector itself, right? The coordinate F2. Divided by the magnitude of F is equal to the sine, this time, of 34.8 degrees. Why sine? Because the F2 is the opposite side in this triangle, right? Opposite to this angle. So as a result, what is that going to give us? If we substitute what we know here, F1 is going to be what? F1 can be solvable by multiplying both sides by the magnitude of F, right? So you're going to get this times the cosine of 34.8. So essentially what I'm saying is that we're going to have 46.3 times cosine of 34.8. Okay? Or I can use parentheses here. So what that should give you is about 38.0 pounds. And keep in mind that this is horizontal, right? Horizontal component. And once again, if you try to find its magnitude, it's going to give you again 38, right? Because we just showed it doesn't matter as long as it's vertical or horizontal, the magnitude will be itself without the bars. Now, for the second component, the vertical component, you can solve it by multiplying both sides of this equation by the bar of f, right? The magnitude of f. You're going to get the magnitude of f times the sine of 34.8 degrees, right? Which should give you 46.3 pounds, right? The magnitude of this vector f multiplied by sine of 34.8 degrees. And that should give you about 26.4 pounds. Okay, this accounts for vertical component. Vertical component of this force that's being talked about. So I hope this was helpful. Thank you so much for watching, and I'll see you in the next video.